what we're going to look at now is the momentum that photons have. Now, it may be a little bit surprising that photons do have momentum, because so far when we've considered momentum, we've used the equation P equals mv, or if we get into relativistic effects, then we've said that P is equal to mv divided by the square root of 1 minus v squared on c squared. Now, in 1916, Einstein proposed that photons, although they don't have mass, do have momentum. And he said that if a photon has an energy given by hf, then its momentum is given by P is equal to hf on c, which is equal to h over lambda, just using c equals f lambda to get that last expression. So now, being good physicists, we shouldn't just trust Einstein, even though he was brilliant. We should say, well, where's the evidence for this? So the first really solid evidence that photons do indeed have momentum came from an experiment conducted by Arthur Compton in 1923. So what we're going to do now is work through the logic behind that experiment and how it shows that photons do indeed have momentum, and that Einstein was absolutely right about the form of the equation he gave us for the momentum of a photon.
Okay, so this diagram here shows the schematic of the experimental setup that Compton used. So what he had here was some target atoms. They were actually carbon atoms, and they consist of carbon nucleuses with electrons around them, which will be an important point. And he shone X-rays with some wavelength lambda onto these target atoms, and then he had a detector, and this measured the wavelength of the X-rays which were scattered, and he measured these at different angles. Now, what we'd expect from classical mechanics is if we've got an electromagnetic wave coming in here and incident on some atoms, then this electromagnetic wave consists of oscillating electric fields. These oscillating electric fields will interact with the electrons around the atom and cause them to oscillate at a frequency equal to the frequency of the electromagnetic wave. And so with the scattered X-rays, the emitted X-rays from our target here, we'd expect these to be emitted with the same frequency as the electromagnetic wave coming in, as that's the thing which is causing the oscillations. So these electrons should effectively be acting as small antennas to retransmit that same wavelength. And that wasn't totally what Compton found. What he did find when this angle was 0, that the transmitted wavelength was at the 71.1 picometers, which was the wavelength of the incident X-rays. However, as he changed this angle, he found that there was actually 2 peaks in the wavelength spectrum, and that the second wavelength detected for the scattered X-rays became increasingly larger as this angle increased. So this couldn't be explained by classical mechanics. However, we can explain it with quantum mechanics. Okay, so to explain it with quantum mechanics, let's imagine here is our electron and here is our incoming photon. Now, this photon, just like in classical mechanics, gets scattered by the electron. So this is before, and then afterwards, the photon's going up at some angle phi here, and that's the angle that we're measuring phi at. And the electron itself is actually also scattered, so it goes down here at some angle theta with some speed v and some kinetic energy k. Now, because we want to conserve energy, our incoming photon has some energy hf and c equals f lambda, where lambda's the wavelength of the incoming X-rays. And our scattered photon up here has some energy hf dash, which is less than hf, as some of the energy of the incoming photon has been given to the electron as the kinetic energy here. So we have hf is equal to hf dash plus K, where K is the kinetic energy of the electron. Now, these electrons can recoil really fast, so we do actually have to account for relativistic effects. So relativistically, the kinetic energy is given by mc squared times gamma minus 1, where gamma is equal to 1 over the square root of 1 minus v squared on c squared. And so we can put this into this expression here, and we have HF is equal to HF dash plus mc squared gamma minus 1, describes the energy conservation for our photon here. And we could also write this, if we wanted, because it will be useful for later, in terms of wavelength. So just using C equals F lambda, if we divide through by F is equal to C over lambda and cancel a C from every term, we can actually write this as H over lambda is equal to H over lambda dashed plus MC. So one of these C's cancelled out because we ended up with C's in these terms as well, gamma minus 1. Okay, so that's our first equation, which we get from energy conservation. Now, as we did similar problems in mechanics, we also considered what was happening to the momentum. So now we're going to consider the momentum again and come up with a couple of expressions to describe the momentum conservation. So let's write energy conservation. Now, because momentum is a vector, we can consider the momentum conservation in two directions. So in this horizontal direction and also in the vertical direction here. So in the horizontal direction, we're going to use Einstein's equation for the momentum of a photon. P is equal to HF on C, which is equal to H over lambda. Okay, so horizontal. The incoming photon has momentum h over lambda, and now some of that momentum goes to this photon which is scattered up here with energy hf dash, and so momentum h over lambda dash, that's its total momentum, but we're only considering the horizontal component. So we need to do that trigonometric bit where we just consider this side. So we multiply this by cos phi, and then the electron also gets momentum. So the momentum of the electron, remember it's going quickly, so we need that relativistic momentum, and relativistically P is equal to mv over the square root of 1 minus v squared on c squared, which is equal to gamma mv. So relativistically we've got gamma mv, and then again we only want this horizontal component, so we're going to times that by cos theta to get our horizontal component. And then, yeah, so this is momentum. And then vertically, well, initially, this photon is traveling horizontally. So vertically, it's got no momentum. And this is equal to, here we want to get this side here. So it's the same expression for this part, but then to get the vertical component, we times it by sine phi. And once this again has the same component for this part, but we'll times it by sine theta. And actually in this case, these need to be in opposite directions. So one's going up and one's going down because I have to sum to give 0. So this is minus gamma mv sine theta. So now we've actually got 3 equations, 1, 2, 3. And we can solve these simultaneously to come up with an expression for delta lambda, how much this wavelength has changed. And you can do this if you want. I won't do it here because it's very complicated, but it's quite fun. So by all means, go ahead and have a try. And this is equal to h over mc times 1 minus cos phi, and this is known as the Compton shift. Okay, so the important point is that we have used energy and momentum conservation to come up with an expression for how much this wavelength should change. Now, Compton did the experiment and he found that his experimental results agreed with our theory. And so this was strong evidence that photons do indeed have momentum, and it is given by the equation which Einstein said it was. Now, there's one thing which may still be puzzling you a bit. If this is the case with all this conservation, then why do we still have this peak at 71.1 picometers? Why isn't it all found at this second peak, lambda dashed, which we've calculated here, how much it's changed by? Okay, and the answer to that is, well, some of the gamma rays are scattering off the electrons, like we've said, but inside the target, there's also these carbon nucleus, and the carbon nuclei are very heavy compared to electrons. So if this M becomes much bigger, then the change in wavelength becomes much smaller. And so this unshifted one actually corresponds to the wavelength of the gamma rays which are scattered off the carbon nuclei, whereas the shifted wavelength here, this corresponds to the wavelength of the gamma rays which are scattered off the electrons around the carbon nuclei. Okay, so hopefully that makes some sense to you, and hopefully that has convinced you that photons, while they don't have mass, they do indeed have momentum.